Hello, everyone. The following is the second in a series of lectures covering Chapter 39. Today, we are going to be talking about sections 39.3 and 39.4. So, as you recall from the last lecture, we've reached the point in history where Newtonian physics and the Galilean principles of relativity didn't really sit well with what Maxwell had to say in his electromagnetic theory. And the Michelson-Morley interferometer experiments, among others, have found that in all frames of reference, the speed of light was always measured to be the value c. It wasn't until 1905 that a young scientist named Albert Einstein stepped in and found a way to consolidate the classical Newtonian understanding of physics with the observed behavior of light. This requires a quick recap of inertial frames. That's just any frame that's not undergoing acceleration. By the way, if you know you're in an inertial frame and someone else is moving with constant speed relative to you, then they're also in an inertial frame. Also, when we talk about events, that's just some occurrence that has some location, some coordinates, and also a time associated with the occurrence. That's all. So, this is what Einstein proposed in 1905. These two postulates are very, 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 very important, and while simple at first, have very strong implications as for how the universe works, and that's not even getting into general relativity. But we are talking about special relativity, so this is what he had to say. The postulate number one states that the laws of physics are the same in all inertial frames of reference. This is in agreement with one of the postulates of Galilean relativity. So there's no preferred inertial frame, right? There's no ether or anything like that. Every frame is fair, and whatever you see relative to your frame is as good as any observation in anyone else's inertial frame. Postulate number two. This one declares the constancy of the speed of light. The speed of light in a vacuum, which is c, is that in all inertial frames, regardless of the velocity of the observer or the velocity of the source emitting the light. So no matter what, in any inertial frame, the speed of light is always c. There's no relative velocity calculations to figure out. No matter how you look at it, you'll always measure the speed of light being c. It's not that, when you see a car down the road, if you go running, that the car seems to be going slower. Not for light. You can never catch up to light. Let's show this, right? Because in classical mechanics, speeds are relative. So if Bob's just sitting on the sidewalk on the right there and he's watching a truck run, and Alice is also running, not on the road, by the way, he can measure the speeds of Alice in the truck relative to his inertial frame. Now, from Alice's point of view, though, she's not the one who's moving. The world is moving around her. Bob is moving behind her at 10 kilometers per hour to the right, and the truck's still moving, although a little bit slower, 70 kilometers per hour to the left. And we can do this using Newtonian mechanics. Now, here's another example, though, after this next slide, that if you were to shine a light while Alice and the truck are running, Bob standing there, they will all measure the same speed of light. They will all measure a value of c. Now, let's look at another example. So, no matter how fast your frame is, no matter how fast you're going, the speed of light that you measure is always c. So, here is the USS Enterprise on the right moving at 90% the speed of light, and the Millennium Falcon is moving at half the speed of light. And they see this big nova explosion happen in the middle of space, and the crew of the Millennium Falcon, Han Solo and Chewbacca, are thinking that, well, we're moving pretty fast towards light, so light should approach us faster. Meanwhile, the USS Enterprise is thinking, well, we're moving pretty fast away from the light, so the speed of light that we should see should be, c minus our speed. So the speed of light that we should measure should be a tenth of c. But their sensors on both ships detect the speed of light to be c. They should have really studied more in their training academy and the physics lectures. So all the inertial frames will agree that the speed of light is always the same. However, they will disagree on things such as events being simultaneous, the length of time intervals, and also the length of objects and distances between 2 points. Let's talk about them one by one. So simultaneity is just this idea that in some inertial frames, events may be simultaneous, so things can happen at the same time. But from the perspective of other frames, they might not see it simultaneously like we do. This occurs when you're in a moving frame that's reaching near relativistic speeds, which just simply means we're moving really close to the speed of light. So let's put it to the test. Alice is just sitting on the ground watching their friend Bob, who's in this single cart train. And the train with Bob's moving to the right relative to Alice. So we are having to be more specific in this chapter when we declare speeds, right? Because Bob moves at a speed v to the right. We could have gotten away with saying that in kinematics or in the mechanics chapters, because the assumption always was that we're always sort of defaulting to a frame of reference that's just on the ground. But since relativity has a lot of like moving pieces and parts, and the frame you're on is really important, really affects how you measure physical traits like time and length, you really have to specify how speeds are being measured. And in this case, we're measuring the speed of the train from Alice's point of view, which is here on Earth. So suppose two lightning bolts strike on opposite sides of the tracks, and Alice is right in the middle, equidistance from the two lightning bolts. So she'll see the light from the lightning reach her at the same time. So she concludes that these two lightning bolts struck the ground at the same time. They're simultaneous. Bob, though, is traveling to the right, and his frame of reference, he's moving closer to the right side of the track. So when the two lightning bolts strike, light from the right bolt will reach him first, and he'll be able to see the right lightning bolt. And then later, because he's moving away from it, light from the left lightning bolt will reach him, and he'll see the left lightning occur. So from his point of view, the right lightning bolt struck first, and then the one on the left. When they meet up after Bob's train ride, they talk about what they saw, and Bob says, "Oh yeah, I saw one in front of me first, and there was one behind me." But Alice keeps saying that they happened at the same time while she was watching Bob on the train. So who's right here? Are they simultaneous or were they not simultaneous? They're both They're both right. Depending on the frame of reference and the relative speed, events may or may not be simultaneous. So consider the second consequence of the constancy of light, of the second the second postulate of Einstein's theory of relativity. This chapter can be a bit of a mouthful, I have to say. So, time dilation. Moving at relativistic speeds has an effect on how we observe time. When you have NASA scientists in ground control monitoring the heartbeats of astronauts who are flying on a spaceship on a mission, it appears that the heart sensors, the heartbeats, appear to be beating slower than normal. The heart seems to be taking longer to beat. So it looks like time slows down inside the spaceship moving relative to the Earth. If the NASA scientists had like a camera in the spaceships and there was like a big clock in the spaceship, they'd see that the clock in the spaceship is kind of ticking pretty slowly. It's running slow. But the curious thing is, though, that inside the spaceship, in the astronauts' chambers, their hearts are beating just fine. Their clock is ticking just like a regular clock does, 1 second per second. Everything's fine. So it seems that these NASA scientists are observing something that's occurring in a different frame, but the people who are in that frame are not experiencing it. Now, consider this other example. There's a tourist back in the time where we had tourism, stands by the Big Ben in London. They look at their watch and they synchronize it so that the minute's hand of their watch ticks at the same time that the Big Ben does. And he feels great about this because now he can say that he's always carrying the Big Ben with him in his little wrist. Now he gets on one of those double-decker buses London is famous for, and it begins to drive away from Big Ben. Now, he keeps looking back at Big Ben, and as the bus drives away, he realizes that his watch and the Big Ben are starting to come out of sync. It looks like Big Ben's ticking slowly. It looks like it takes more than a minute for the minute hand to move. So, in other words, it appears that the time between the ticks in the Big Ben is expanding in the same way that a pupil dilates. This is why we call this phenomenon of observing clocks to run slow for things outside their frame to slow down. We call this time dilation. So the measurement of time intervals can change depending on the frame of reference of the observer. And this, again, this is an effect that it's only observed once you reach speeds near that of light. We'll see that soon. But first, we need some vocabulary. We're going to define, since we're going to be measuring time intervals across different frames of reference, we need to define the proper time. This is delta tau. It's a Greek letter tau. And this is a time interval between two events measured by someone who's seeing the events occur at the same location. So if I'm driving a car, I can measure the proper time of anything that's happening in the car because everything in the car is moving with me. If I'm the tourist watching Big Ben on the ground, then I can measure the proper time of Big Ben since I'm seeing the ticking of Big Ben happen at the same spot. However, when the tourist gets on the bus and the bus drives away, the tourist can't keep proper time of Big Ben anymore because he's moving farther and farther away from Big Ben every second. So he's not seeing the ticking of the clock occur at the same spot from his point of reference on the bus. So if you're an observer like the tourist on the bus watching events occur at different locations, what you measure is a time interval, which is called a delta t, that is always going to be longer than the proper time. So this is what happened when the tourist saw Big Ben tick slowly while he was inside the bus. This is time dilation. And the amount that heartbeats appear to slow them by, the amount by which clocks appear to tick slowly by, is determined by the Lorentz factor, the Greek letter gamma, which is related to the speed of the frame the observer is on, who is measuring the regular time interval. So the amount that time dilates is equal to a product of the proper time of the time interval. So again, this would be something that you can only measure if you are seeing the events all happen at the same spot. So if you're standing at rest relative to, to like the clock or the astronauts or the Big Ben, then you measure proper time. But for someone who's in a moving frame, what they actually measure is a product of the proper time times the Lorentz factor. And the way that the Lorentz factor works is that it rewards you for moving at relativistic speeds. The formula is 1 over the square root of 1 minus a ratio of the speed of your frame over the speed of light. So for most vehicles, for most moving frames we have, cars, planes, trains, automobiles, this factor is basically equal to 1. The effect of time dilation then is barely noticeable, since proper time and the observed time interval are basically the same if gamma is basically 1. But as we move closer to relativistic speeds, such as being on the Millennium Falcon or the USS Enterprise, then we get to observe that outside our frame, outside our spaceship, time gets dilated. And so time intervals will always be greater than, or at the very least, equal to the proper time. So here we're going to see the Lorentz factor as a function of speed. And basically, for most everyday speeds, the Lorentz factor will be 1. Basically, if you're in a moving frame that's less than 10% the speed of light, Lorentz factor really won't matter. You won't really notice time dilation. So if you have 2 frames and the relative speed is less than about 10 million meters per second, then the difference measured in time intervals will be negligible. As you can imagine, most things in the everyday world don't move faster than 10 million meters per second, so we're mostly in this region. But the Lorentz factor, though, does tend to increase once you reach about a speed that's about 85% the speed of light. Time will dilate by a factor of 2, which means that when you're moving at almost 85% the speed of light right here, it means that time intervals that you observe outside your own frame will be slowed down by a factor of 2. So if you're on a spaceship flying away from Big Ben at 85% the speed of light, then the ticking of Big Ben will appear twice as slow for you. The interesting thing is that time dilation occurs for all inertial frames because the speed is relative. So a stationary observer and a moving one would measure each other's clocks as running slow. The astronauts would see time dilate in the NASA control room, and the people on the street will see that the tourist on the bus has a slow watch. So for the people on the street, Big Ben's doing fine, but on the bus, which would have to be a relativistic bus moving really, really fast to really notice it, but people on the ground by Big Ben see that on the bus time is running slow. Because again, the speed is relative. If you're in a really fast moving bus, you are not the one who's moving, it's the world around you who's moving behind you really fast. But obviously the people on the ground, it's you on the bus who's moving fast to the right. So time dilation is a two-way road. It's just something that you observe, that 2 frames observe on each other. So let's do a quick example involving a nondescript man in a red suit and beard and reindeer traveling in the skies. We have a grandfather clock here. You know how much I love to have questions with grandfather clocks, and the period of this, the bob of this grandfather clock's pendulum is 3 seconds in the reference frame of the pendulum. So someone standing on the living room will notice, oh yeah, it swings, every 3 seconds. But what about this mysterious man who's moving through, and he's moving at a speed of 96% speed of light, thanks to his relativistic reindeer? What would he measure? Well, so because he's moving really fast, from his frame of reference, everything around him, time intervals are being dilated. And relative to the pendulum, right? He's moving at 96% the speed of light, so he's going to see the pendulum tick slowly. The bulb's gonna go swing slower from his point of view, which means that a period would take longer to complete. It would take longer for the bulb to do a full cycle. It's also worth mentioning that from the man on the sleigh's point of view, it's the pendulum that's moving to the left at 96% the speed of light. But from the pendulum point of view, the man's moving to the right. So if you're standing by the pendulum and you watch the man fly by, from your point of view, it's the man on the sleigh whose time is being dilated. If the man had a watch on him, you'd see that his little watch is ticking slowly. Anyways, from observer's frame at rest for the pendulum, the pendulum is moving past him at a speed of 96% the speed of light. So the proper time of the pendulum, again, is what you measure if you're at rest with it. So it's 3 seconds. So the time dilation measured by the observer, the man with the sleigh, is the Lorentz factor times the proper time. So the Lorentz factor in this case ends up being about 3.67 because the speed is pretty big. And so the period of the pendulum as observed by the man on the sleigh is actually 10.7 seconds. This is much longer than the proper time, which makes sense because if you're moving really fast, everything around you, including the pendulum, is going to go slower. Now, muons, which are particles that share a family with electrons, are often coming in from outer space. They're part of all the cosmic rays that kind of fall into the atmosphere all the time. And they really don't interact much with matter. They don't really get in the way most of the time with any sort of technology, unless you're working with like telescopes or radars, and perhaps muons can bug you. But all intents and purposes, muons are just particles with a short lifetime, and in fact, so short that their average half-life is 2.2 microseconds, at least measured, at rest with a muon. Now, if you're standing on the ground, the muon's going to have a longer lifetime because you are watching this muon, which moves really, really fast. So its lifespan is dilated from your point of view. If you're, getting a saddle and riding the muon down to Earth from space, then on the muon's frame, you'll see that, in about 2.2 microseconds, the muon decays. But if standing on the Earth, the muon's seemingly going to live longer. So we can actually measure from a observer on Earth how long the muon takes to decay. The Lorentz factor for a muon moving at 99% the speed of light is 8, which means that the lifetime of the muon, as seen by observer on Earth, is 8 times the lifetime of a muon in proper time. So it lives on average 17 microseconds, which is actually enough time for the muon to and this is specifically talking about muons created in the atmosphere during cosmic ray showers. So basically, a muon created in the atmosphere, its proper time, its proper lifespan of 2.2 microseconds isn't enough to reach the ground, but it appears to us that the muon lives 8 times longer than what's expected. So that gives it enough time to reach the ground. But from the muon's frame of reference, their decay time is still only 2.2 microseconds. So from their point of view, how are they reaching the ground? Well, it turns out that from their point of view, the distance to the ground is actually much shorter due to their relative motion. than the distance that we measure on the Earth. And that is the effect of length contraction, which we'll talk about soon. But first, let's go into this very famous example of relativity called the twin paradox. The so-called twin paradox, which is not actually a paradox, it just looks like one, is one of many quote-unquote paradoxes that occur when we don't properly understand everything that's happening in a situation with relativity involved. So this twin paradox goes as follows. There's two twins. There's Speedo and Slogo. They are both 20-year-old. They're both young men, and Slogo likes to chill at home, works at a bank, but Speedo is part of the Canadian Space Association, and he's off to fly to Planet X, and the whole journey has been charted out. And if you fly to Planet X and back, that should take you 42 years. The state-of-the-art spaceship that Speedo is flying off can move at speeds that are about 95% speed of light relative to the Earth. So while Slogo's chilling at home, he'd see his twin brother Speedo take off at really fast speeds towards Planet X. And the mission goes off without a hitch. So Speedo reaches Planet X, and as soon as he does, he immediately turns around and sets the thrusters back to Earth. And the same speed now, 95% speed of light, pointed towards the Earth. Once Speedo returns, he's found that his twin brother is a lot older than him. Kozlo has aged by 42 years. He's a 62-year-old man, but Speedo is only 33 years old at the return of his journey. So, what's happening here? Why this one twin older than the other? Why is it that the twin who got to go on a spaceship to Planet X and come back only aged 13 years, while Slogo, who stayed at home, aged for 3 times that? Well, here's the thing. 42 years passed for Slogo, but only 13 years passed for Speedo on his ship. The paradox is that due to the speed of the ship being relative, from Speedo's perspective, it's Slogo on the Earth's frame who are moving behind him at 95% the speed of light. So, basically, what Slogo sees over those 42 years is that Speedo, the time on Speedo's ship is dilated. So, effectively, only 13 years pass on the ship as observed by Slogo on Earth. But we'd expect that then from Speedo's point of view on his ship, it's Slogo that's moving away from him. So from Speedo's point of view, he'd see that the actual time that's passing on Earth is also 13 years. So basically, there'd be this sort of time dilation that's equally measured by both Speedo and Slogo, but then they'd both be saying that, well, okay, then my other twin's going to age more slowly than I will because time's dilating outside my window. So the thing is, though, is that if that were true, then if both of them are aging more slowly, then when Speedo comes back, they would be the same age. They would have both only aged 13 years. But what actually happens is that only Speedo got to age slowly while Slogo aged 42 years. So the reason this happens, it's not a paradox at all, because only Slogo was in an inertial frame, and only Slogo can then properly measure the time dilation. He can properly measure that in the observing the moving ship, that with the speed that the ship moves at, then in the 42 years that it took for the ship to fly to planet X and back, Slogo then calculates then the time dilation is a factor of 3. So the 42 years that he spent on Earth on the ship come back to just 13 years. So basically, he's figuring out the proper time on Speedo's ship, not shift, Speedo's shift. I always keep saying shift. I said, corrected myself and then said the same thing again. Shift, ship. Anyways, so Slogo is able to properly measure the time dilation in Speedo's ship because Slogo is in an inertial frame. And he figures out that if 42 years passed for him on Earth and the ship is moving at 95% speed of light, then there's a time dilation factor of 3, which means that he's measuring time 3 times more slowly, which means that on the ship only 13 years have passed. Although I'm realizing now that the factor is a bit more than 3. But essentially, 13 years have passed in Speedo's ship as measured by Slogo. Speedo can't really do the same thing. He can't really go and measure time dilation properly while he's on his journey, because he's not actually in an inertial frame. Speedo at one point stops at planet X, turns around, and keeps driving back to Earth. So he's switching frames halfway through the journey. And so that way you can't just use one time dilation formula to figure it out. And here's a nice video from TED talking about the twin paradox in good detail. The twin paradox is a bit of a puzzle, something that takes some sort of studying and kind of analyzing to really digest. So, give yourself the time when studying to look at the video, look at a few examples, and just kind of, at the very least, be able to understand why it's called a paradox and why it's actually not. So this stuff is a bit tricky, but with some practice, it does become easier. Now, I want to talk about one more thing, which is another consequence of the speed of light being constant, which is length contraction. So different observers can measure events occurring at different times. They can also observe clocks running slow, and they can also measure lengths differently. If you're driving down the road and I'm just sitting on my porch and we both see a skyscraper, to you and me, despite that we're in different frames, you're in the car, I'm on a rocking chair, we're probably both agreed that the skyscraper, is about the same height. But once we start getting to relativistic speeds, it turns out that the size and distances of our surroundings tend to change as we move faster and faster. So to talk about that, we should first define a proper length like we did with time, and then we're going to define a proper length. And that's just the distance between 2 points as measured by an observer at rest relative to both points. So remember the muon example. If you are standing by a mountain, then you can measure the proper length of the mountain. The muon, though, doesn't get to measure the proper length since it's moving relative to the mountain. So if there's an observer that's moving with a speed along the 2 points that make up some measurement of a length or a height, then the distance that they see from their frame of reference will be shorter than the proper length. And this is saying that, for the muon that's moving towards the Earth, they will see the mountain shorter than what it actually is for an observer on Earth. So this decrease in observed length by a moving observer is called length contraction. So this is an interesting thing about the muon, that from Earth's point of view, from observer on Earth, we look at the muon and we don't get to measure the muon's proper time. We only get to observe its dilated time, which means that to us, its lifetime is longer than it should be. It's about like 8 microseconds. And we do get to measure the proper length of the mountain. Now, on the muon's reference frame, though, the muon doesn't experience its own time dilate. We observe time dilation, we don't experience it inside their own frames. So the muon's frame, the muon still has a lifetime of 2 microseconds. And what they observe, though, is the length of the world around them contracts. And from their point of view, they only have 2 microseconds to reach the ground, but they can because the mountain they have to drop down through is contracted. And the way that you measure by how much something contracts by is you take the proper length, you divide it by the Lorentz factor. So the faster you move, the more things contract around you. Now, obviously, this depends on the Lorentz factor. So for non-relativistic speeds, the amount by which things contract is super, 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 super small. Once you get to more than 10% the speed of light, that's when length contraction really begins to become noticeable. So that's why we're not going to see a building get shorter if we're on a plane anytime soon. But it's interesting that theoretically, the space ball, if thrown at relativistic speeds, will get flatter and flatter and flatter. We will observe it to get flatter. So when things move really fast, we see their length contract. From their point of view, though, for a fly on this baseball, though, the fly will notice length contraction. If it's moving relative to the baseball, then it'll notice everything around it contracting, but not the baseball. And it's also worth mentioning that contraction is only going to happen in the dimension of motion. So for the muon, only things in the direction of the muon's velocity will things contract. So it'll see the height of the mountain contracting, but it won't see clouds shrinking horizontally or anything like that if it's just falling down. And like time dilation, like I was saying, length contraction is observed by both frames. So if we're on Earth and we are watching Major Tom on a spaceship here flying to Alpha Centauri, from our point of view, we can measure the proper length to Alpha Centauri. What we can't measure is the proper time on the spaceship. We can only measure a dilated time because we can only measure proper time on Earth since that's the frame. Now, the spaceship is moving really fast, so to us it looks contracted. From the spaceship's frame, though, it's everything around them that's moving at relativistic speeds, so everything around them appears contracted. So much like time dilation, it's not something you experience in your own frame, but you observe around everything that's not moving at the same speed that you are. So everything is not at rest relative to you. Everything outside your frame, you will observe its time dilate and its length contract. So from the Major Dom's point of view, space around him is being contracted. The distance between Alpha Centauri and Earth is contracted. The Earth looks contracted horizontally, so is Alpha Centauri. And his watch on a spaceship is ticking properly. He gets to measure proper time in his own frame. So let's go back to the pendulum question. A grandfather clock has dimensions of about a half a meter by 2 meters. And The mystery man keeps flying by. And the question is, though, what dimensions would he say the pendulum have if he flies back at relativistic speeds? So we have the proper length of the grandfather clock in both dimensions. Horizontally, it's half a meter. Vertically, 2 meters. And we know the Lorentz factor, given the speed, would be about 3.67. So we expect then objects to contract along the direction of motion by a factor of 3.67. And you also expect that clocks will run slow up by a factor of that 3.67 as well. So the observer, the man in the red hat, from his point of view, the grandfather clock is moving to the left with a speed of 0.96 times c. So he'd see the clock shrink horizontally by a factor of 3.67. So we divide the proper length by gamma. We get about 0.136 meters. So definitely the clock has shrunk from the point of view of the man on the sleigh. Because the relative motion, though, is not happening along the y-axis, there's no change. It's still measured that the clock is 2 meters tall. So in kinematics, we've drawn a lot of position versus time graphs. And we're sort of going to go back to that to show how different objects are moving when it comes to special relativity examples. But since we're talking about objects, moving near relativistic speeds, near the speed of light, it's more useful to create space-time diagrams or space-time graphs rather than just using position versus time graphs. So unlike position versus time graphs, these space-time diagrams have the position axis being horizontal. So in this case, it's just one direction. It's just an x-axis. You'll see some other graphs will also have like a y-axis on a third dimension. But overall, the vertical axis corresponds to time, and there's a factor there of the speed of light c on the axis, and that's just there to scale things a bit so that what you can have then with the time axis scale by c is you can have the two lines here that you see. These are drawn in most space-time diagrams, and these two light beams represent light. This represents a path of light through the space-time diagram. So basically, the idea is that what you're seeing in this light beam is light traveling over time. So right, as you go up on the space-time graph, time is moving forwards, and as you go left or right, space is you're traveling in that direction across space. So then this is telling you that as time moves forward, the position of light changes and it moves farther and farther away from the origin in both directions. Now, because the graphs here, it's position and time, then their slope would effectively tell you the velocity. So because nothing can move faster than the speed of light, then any world line that we draw would fall between these two light beams. And a world line is, again, it's just how someone's position changes over time. So what we see here is actually two world lines for the twins. So for Ghostlow, who stayed on Earth the whole time, we see that as time moves forwards, his position's not changing. He's just staying in the same spot. For Speedo, though, he's been moving to planet X, and then he came back. So as time passes, he's moving farther away from the origin, from Earth, and then at one point he reaches planet X, and then he turns around and comes back to Earth. Note that his speed, right, was close to the speed of light, but not quite. So he's obviously not below the light beam. He's obviously above it, and you can't have a world line that goes underneath these light beams, because that will mean moving faster than the speed of light. So here's an example from the textbook. An astronaut moving to Sirius, and it's a distance of 8 light years from Earth. A light year is basically how much light can travel in 1 year. So it's a very, very, very big unit of measurement. And the astronaut charts it out, and he measures that his one-way journey is going to take him 6 years. The spaceship can move at a speed of 80% the speed of light. So the question is, well, if it's a distance of 8 light years apart, but the astronaut's saying, oh yeah, I can do that in 6 years, but it takes light 8 years to get there, who's going to do it in 6 years? Well, the thing is that from the frame of the spaceship, the distance is contracted. So you can actually figure out the length contraction of the distance between the Earth and Sirius. The distance will be contracted so that the total distance traveled in the space by the astronaut, from his point of view, is just 5 light years. So in 5 light years, that distance is short enough that he can make it to Sirius in just 6 years. So what if you're in mission control and you're keeping an eye on the trip to Sirius, and you made a deal with the astronaut that as soon as he arrives in Sirius, that he'll shoot a light flare to signal that he's arrived. So how long is that going to take? Well, the astronaut said that I was going to say the astronaut can make it there in 6 years, but if we consider the light, though, if we consider that from the so let me start from the beginning. So we know that Sirius is 8 light years apart, and we know how fast the spaceship goes. So from the astronaut's point of view, from the technician's point of view, it should take you 10 years to get to Sirius, moving at 80% speed of light. Now, once the astronaut gets to Sirius and shoots the light, then the light has to travel 8 light years, so that's going to take 80 years to get back to Earth. So it's going to take 8 years total since the astronaut leaves Sirius for the light signal to reach the Earth. One last thing to talk about for this section is the relativistic Doppler effect. So if you recall, when we talked about the Doppler effect of sound, which was when sounds from moving cars would sound like higher or lower in pitch, depending on whether they were driving away or towards you, then we had to consider the speed of the source of the sound. We also had to consider the speed of the observer, but also we had to consider, that there was a medium that was propagating the waves. For light, though, there's no medium of propagation. So there's no middle frame to compare the observer and the detector. We can only really talk about the relative velocity between the source and the observer. And either way, though, in the same way that sound waves can undergo this Doppler shift, so can light waves. If the source of light and an observer approach each other with some relative speed, then the apparent frequency as measured by the observer of that light will be different than what's being emitted. It's the same idea as we saw for the Doppler effect for sound waves. If you're moving towards the source of sound waves, the waves are going to be coming at you faster, you're going to absorb a higher frequency. The same thing happens when you're moving towards a source of light. The observed frequency of light is going to appear bigger than what it actually is in the rest frame. And again, because there's no middle frame like there is for sound, the formula just depends on the relative speed b between the source and the observer. So when the observers approach each other, the formula will show you that the observed frequency is higher than the actual frequency. And when you consider the spectrum of visible light, right, the light with lower frequencies tend to be redder colors, and with higher frequencies are blue. Therefore, when there's a Doppler shift towards a higher frequency, we call that a blue shift, because if you're moving towards a source of red light, it'll appear to be bluer. However, when you and the source are moving away from each other, then in the formula you have a negative value for the relative velocity, and so the shift that happens is that the frequency that you observe of light is lower than what's being emitted. This will make green light redder, blue light greener. This is called a redshift. This is something that has been noticed in stars throughout the galaxy and beyond that in space, where we expect the light of certain galaxies and stars to be in a particular range, but we're noticing that it is redder than it should be. We're noticing that the light of these stars is redshifted. That means that us and the distant stars are moving away from each other, and this was one of the bigger hints towards understanding that the universe is expanding. Since the galaxies are moving away from one another, their light appears redshifted. Another cool example of the Doppler shift for light is in finding exoplanets. So it's not just the solar system that can host planets like the Earth or Mars or Venus or Mercury, terrestrial planets. There is many systems that host what we call exoplanets, and they're a bit hard to detect since they're not like the stars that emit their own light, and they're usually so much smaller than the stars they orbit around that it's very hard to detect them even if they are reflecting some light. But what's interesting though is that exoplanets in their own little star system, they'll have small gravitational tug on the star that they orbit. So the star at the center of that system has its own little rotation, has a little orbit, and by measuring the light from the star over time, you can see a blue shift when the star is orbiting in a direction towards the Earth, and you see a red shift when the star is orbiting in a direction away from the Earth. So you can see in the graph here, as the star is orbiting a little bit due to the exoplanet in its system, it's this part of its revolution, it's coming towards the Earth, so the light appears shifted to a higher frequency. It's blue, but here it's moving away from the Earth, so it appears red. And with that information, that's actually tips you off that the star has a bit of an orbit. That means that its gravity is being tugged by some exoplanet or some other body. And with that information, you can actually figure out the size and location of the exoplanet. So exoplanet searches take advantage of many relativistic effects to find new and exciting planets, and it is a very popular topic, especially in astronomy and astrophysics, since more and more optical instruments and telescopes have been developed with better imaging technologies that allow us to really map out the systems around us, not just the stars, but also potential planets that surround them. Anyways, that's all for this lecture. So I hope you join me next time where we will be talking about the Lorentz transformation equations. Until then, thank you.